So you guys all have your test back. That's great. Also on Tuesday, I checked in problem sets again. Always recommend that, like that first day of the week that you check your grade and make sure that if you did turn something in that I ended up seeing it, marking it. We have a week's grace period to kind of get things squared away if there was a mistake or we forgot or you didn't sync or there's a technical oopsie. But just as a reminder to try to check your grade that first day that we meet during the weeks, if you had anything due over the weekend, to make sure that I saw everything and got it updated. Today we're going to be starting Chapter 7, which is the beginning of a series of chapters involving statistics. No, Tori, it'll be totally fine. These chapters consist mostly of definitions and calculator literacy. So there's not a lot of by hand calculation that we'll need to be doing. Mostly it's going to be getting things set up and understanding what's being asked. So it's a lot of just do you know the vocabulary? Do you know what stuff means? And then do you know how to do that on your calculator? Very calculator driven. But even before we get to the calculator parts, we got a lot of vocabulary to kind of grind through, and that's what we'll start today. Chapter 7 is going to be mostly kind of like vocabulary and interpretation kind of thing. So there's not a lot of computation that we'll be doing here. But that's what we're starting today is Chapter 7. So Chapter 7 is all on descriptive statistics. And here we go. So when we talk about statistics, that's the science of data. In statistics, we're often interested in doing some kind of data analysis. So that's the process of organizing, displaying, summarizing, and then asking questions about some data set. And just as a reminder here, all these PowerPoints that we're looking at are on My Notre Dame in the download section. So all the Chapter 7 PowerPoints, all the Chapter 1 PowerPoints, they're all there. So if you want to sit and listen, because you know that you have the PowerPoint, you're fine to do that. If you're like, I can't sit and listen and pay attention, I need to write stuff down, I understand. Just reminding you, again, that if you're like, I'd rather not have to hassle with writing anything down because I have the PowerPoint, that is okay. All right, continuing on. When we talk about doing data analysis, there's two things that we're typically concerned with. That is the population which we're studying. So that's the group of individuals that make up our data set. And then the variables, so that's some characteristic of that population. So for example, if our population is cars in the parking lot, the variables we might want to study could be like the color, or the make or model, or mileage, or fuel efficiency, or whatever. Number of dents. Could be all kinds of things. Could be a variable if we're analyzing the cars in the parking lot. If our population is students in the class, we could be interested in, gender or hair color or GPA or number of texts sent in the last 24 hours or favorite color, all kinds of things, right? Everybody cool? Difference between a population and a variable? Okay. Now, a variable is typically split into two categories. You have qualitative variables. So that's like a description. So like colors are qualitative, right? If we're talking about the color of the cars in the parking lot, or quantitative. So quantitative variable is a number. So if you're looking at the gas mileage of the cars in the parking lot, that's a quantitative variable, because the gas mileage would be like 22.6 miles per gallon or something like that. Everybody's cool? Quantitative versus qualitative? Should be easy to remember because qualitative sounds like quality. Quantitative sounds like quantity. A quality is a description, a quantity is a number, right? So when we talk about quantitative data, we typically split that into two types. So there's discrete data. So if we're looking at like the number of red cars in the parking lot, that's discrete data because you can't have like half of a red car. It's either a whole red car or not a whole red car. And the other type would be continuous. If you're talking about fuel efficiency, miles per gallon, well, depending on how you want to measure that, that fuel efficiency could go as many decimal places as you wanted to measure it, right? It could be 22.5 miles per gallon or 22.51. Or maybe we rounded the one, so maybe it was 22.52, and you just could go on forever, right? You could have literally any decimal answer for that. Everybody's okay? Can somebody else give me an example of a variable that would be discrete? So let's say the population of students in this classroom. Joey. So that would just be, that's not a variable, that's going to be that's part of the population. But you could say the number of male or female students would be discrete, right? Like that's going to be a whole number. You can't have like, oh, I'm only count as half, right? It's either you're whole or you're none, right? What's an example of a continuous variable if we're talking about students in the classroom? How about height or weight? Depending on the tool you're measuring, you could get as many decimal places for an answer as possible, right? Like this person is 1.7326453298 meters tall, right? Like you could go on forever if you have a measuring stick accurate enough. Everybody's okay with that idea? Okay. So discrete are things that you have to count with whole numbers. Continuous are things that could be any decimal. All right. And a note here that qualitative data is always discrete because it's like either red or not, or it's blue, but there's not like some color that's in between, right? It's just like, no, that's a new color. That's not something that's like red and a half. You know what I mean? It's like red is red. If it's not red, it's a different color. It's not like red 0.5. So a variable, again, when we're doing this data analysis, should take on many different variables. Oftentimes, we're going to be interested in the number of times or how often a variable takes on a specific value. If we look at all of the times that a variable takes on a given value and how often it takes on that value, that's called a distribution. So if the variable we're talking about is the gender of students in the classroom, that distribution would be like 10 males and 11 females or something, right? That's our total distribution for the 22 students or whatever we have here. You guys feel okay with that idea? If it's like the make of cars in the parking lot, you could have like, there's 36 Fords and then 19 GMCs and 12 BMWs and whatever, like that would be the distribution. Just a list of the different different values the different values the variable can have, and then the number of times that a thing from our population takes on that value. You know what I mean? So here is a distribution. So it has the model for the car, so the make and model, and then the miles per gallon. So our value of interest was the miles per gallon. So one way we might represent that distribution is with something like a dot plot, where the x-axis here is the different miles per gallons. And every time I get a car that has 25 miles per gallon, I put a dot. So like I got a dot from the Cadillac CTS, and then I got a dot from the Jaguar XF, and then we got a dot from, missed one somewhere apparently. Whatever. You get the idea though, right? So this chart and this dot plot represent the same set of information, right? It's representing just the data's, one is visual and one is a tabular. Okay with that? Okay. So in statistics, we gather data, we analyze the data, we'll explore what's going on. So we'll often want to examine the variable by itself, and then we'll also want to examine its relationship between variables. So like, is there a difference in the fuel efficiency between, like GMC cars and Ford cars or something? So typically when we do this, we want to start with a graph to give us a visual idea of, can my eyes detect anything obvious going on? And then we'll move from there to a numerical summary. So, okay, my eyes seem like there's something going on here. Can I do a statistical, like a number crunch, to kind of verify what I'm seeing visually? It's the typical sequence of what we do is in the real world when you're doing an experiment. Let's look at some graphs, and then, oh, look at this weird graph we're getting. This certainly seems like something's going on here. Can I verify that now numerically? And sometimes you can and sometimes you can't. And we'll talk about like the how and what's of this. This is just kind of outlining the process in generalities here. So it's going to feel very vague right at the beginning. The point here that we're getting at or trying to get at is like the sequence of workflow. Not how to actually do any of that work, but just kind of the sequence of workflow. Do you guys get what I mean here? And we'll go into all kinds of gory details about how to represent things graphically and how to do numerical statistical analysis, but not yet. So at the end of our data analysis, what we want to have is some kind of inference. What can we say about this population based on the data analysis that we did? That's what we mean by an inference. So we start with some population, and we'll take a sample of that population. So most often, measuring the entire population is like just infeasible, right? If we want to look at, like the distribution of high school seniors and their gender, well, I'm probably not going to be able to survey every single high school senior in the country to get that information. What we might do is just look at a sample, like the students in the NDP senior class, and then say, oh, look, tends to be, we've measured more female than male students here. Maybe we'd say, in general, there's more female high school seniors than males, right? That's what we mean by a sample. So we're going to take a sample. collect our data from that representative sample, analyze that data, and then make an inference about the population in general. So again, if our population is high school seniors, our sample could be the high school seniors at NDP. The data we might collect from them is just their gender or biological sex if we're going to live in like a kind of a complicated world. And we can perform some data analysis and then say we find that there are more biologically female students or seniors at NDP than males. We could say, in general, we believe that to be the same for all seniors everywhere. That's our inference, that we make a claim about the entire population. You guys kind of see the idea? This is in general how statistics works. And really most real world like measurement. Like this is how political forecasting works. Most of our business decisions are made this way. So there's three kind of terms that I want to make sure that we have a good definition for. So we have a population, a census, and a sample. So a population is the entire group of individuals we want information about. And when we say individuals, that could be like people or it could be like objects, right? Could be like, 2024 Ford Broncos or something. Could be our individuals. Everybody's okay with that? A census, then, is a collection of data from every individual in the population. Extremely difficult to do a census, extremely expensive to do a census, very time-consuming, very resource-intensive to measure every single individual, right? The United States does a census like every 10 years. The reason it only happens every 10 years is it really takes a long time to kind of get it done and then a long time to analyze what's going on. It's really expensive. We pay a lot of government employees to go out and collect people's surveys back, right? In the Bible, like Jesus is going to Nazareth for a census, right? That's why they're going back to Nazareth, even though that story seems apocryphal because that's not how the Romans did their census. But, anyways, a sample is just a subset of the individuals from the population that we collect data from. Almost all decisions are made from samples rather than census, right? If an automotive company wants to decide whether they need to do a recall because they think they have a defective, something's defective on their automobile, they don't check every single vehicle coming off the assembly line. They inspect, some sample of them and look at the rate of failure for that part and then decide whether they need to issue a recall or not, right? For political forecasting, we have an election coming, right? They say that candidate A leads over candidate B by 3% in this state. They haven't surveyed all possible voters in that state. They've taken some sample and then they're making an inference based on the outcome of that sample, right? Everybody feels okay on this verbiage? Okay. Oops. So you can create you may want to build your sample according to a certain parameter. So, for example, if you're doing political forecasting and you're interested in how candidate A is viewed by the portion of the population with income levels above $250,000 a year, that income level could be a parameter inside the population of voting age individuals, or eligible voters, I should say. A statistic is a numerical. Oh no, I'm sorry. Let me rephrase. So that was a bad example, and I gave you a parameter. So parameter would be like, like nationwide, like 68, or I would say 54% of all college students are female, right? A statistic would be, in our sample of 10,000 college students, we found that 56% of our sample were female. So the parameter applies to everybody. The statistic applies only inside of your sample. Now, if you do a good job of building your experiment, you hope that your statistic is the same as the parameter, right? But you never really know. You can have more certainty, but you're never really going to know. So inferential statistics is a statistic you use to make an inference, right? So it's just something that we're going to try to apply to the entire population. So again, we start with our population and some sample of the population. We collect the data from that sample. Notice I wrote representative sample. That's the best kind of sample, is that our sample is like similar in demographic to our population as a whole. For surveying, like eligible voters, and our entire sample is from one party, that's not very representative. And then from that representative sample, we're going to make an inference about the population in general. Same kind of idea we've looked at. The benefit of collecting a sample instead of doing a census is just cost. A sample is going to be cheaper and more time, or less time consuming to survey than the entire population. Now, if you want it to be representative, that still takes some effort and still costs some money, but way less than trying to get everybody. You know what I'm saying? Now, if it's something where the population is small, if you're looking at, the average acceptance rate of the top 100 colleges in America, you could do a census of that. There's only 100 colleges. That wouldn't be terrible. Now, if you're looking at the average acceptance rate for all colleges and universities in America, that's rough. That's going to be a lot of data to collect there. Probably don't want to do a census there. Okay, moving on. So choosing a sample, the way we choose a sample is extremely important and can destroy the validity of any inference that you want to make. If you have a poorly constructed sample, it's going to be your inference is going to be cockaboo, right? If I am looking at the average height of high school students and the only students I sample are on basketball teams, am I going to get maybe make a good inference? No, right? Who are the tallest, the tallest individuals at any school typically end up on a basketball team, right? I'll say typically, because certainly there's like well, so-and-so's like 1,000,000 feet tall and they don't play basketball. I'm like, okay. But you're going to be way taller than normal. And then average, maybe. Normal's a bad word to use there. Okay. So, how do we want to choose our sample? So you want to start by defining the population you want to describe. Whether that population could be, like cars produced in the year 2024, could be high school students, could be, single men over the age of 50 who make between $50,000 and $100,000, who have a cat and last name starts with J. Could be really specific of a population, but that's maybe what you're interested in. It's a bonkers thing to be interested in, but, everybody else kind of get the idea? Identify population. You want to say exactly what you want to measure. So what are you trying to learn about this population? In the case of your cars built in 2024, maybe you want to look at the average fuel efficiency, the miles per gallon. If it's high school seniors, maybe you're looking at the number of colleges applied to. If it's our single gentleman with the last name J and all those other attributes, maybe you're interested in his opinion of Charmin toilet paper or something. Right? Could be like anything that you're interested in. Now, once we know what we want to measure, we want to survey that sample in order to learn about what we want to measure. So a sample survey is just a study that uses some organized plan to choose a sample that represents some specific population. And the last one is, how are we actually going to do the choosing, right? We're going to make a plan to choose our sample, but how we do that choosing is even matters, right? So looking at ways to do that, can somebody grab the door here before the lunch crew comes and makes a whole mess of noise for me? Thanks, Geraldine. So how to do sampling well. The gold standard in sampling is a truly random sample. By randomizing the sample, we rule out favoritism and self-selection. So any type of random sampling is going to involve using a chance process to determine which members of the population are included in the sample. Some ways of doing that might be we assign every member of the population a number, and then we use some kind of random number generator to select the individuals. That random number generator could be like a mechanical, like a machine, like your computer, or it could be like drawing names out of a hat, or like lottery balls, that kind of a thing. Could be lots of ways of doing that. One type of random sampling is called a simple random sample. In this case, every group of individuals in the population has an equal chance of being selected for the sample. And in general, in practice, typically you'll use some kind of computerized random number generator to do that selection. So random sampling is our kind of our gold standard. And a simple random sample, every member of the population has got an equal chance of being selected. So to make a simple random sample, we number each individual in the population and then use a random numbers generator to select the individuals for our sample. If we need 100 people, then we select 100 random numbers, and those correspond to the people or individuals for our sample. If we want 55, we take 55 random numbers, or what, you get the idea, right? Draw 12 names out of a hat. You have Mr. Kulik use his random number generator or random student program to pick your random students. Another type of random sampling is called a stratified random sample. So what that means is that we're going to classify our population into groups of similar individuals called strata, and then we choose and we do a separate simple random sample in each stratum and combine these to form the sample. So for example, if I want to make sure that my sample has the same number of men and women in it, I might take my population and separate it into two strata, men and women, and then take, random 50 from one strata and a random 50 from the other to make sure I have the same amount of men and women. Does that make sense there? Or if you're trying to simulate like the income distribution for a city, you might make sure that, if you're taking 100 individuals, you want like 12 low income and 70 medium income and then like 18 high income, so that it matches. You're guaranteed to match the demographics for your city if what we're studying is directly related to income level. You kind of get the idea? Another type of sampling is called systematic sampling. So to get a systematic sample, we basically just are going to pick every kth individual. This is frequently used in like consumer goods. Like if you manufacture something and you're doing like quality testing on your product, you don't inspect everything that comes off your assembly line. You might only inspect every 100th item or 1,000th item or 10,000th item, depending on what it is you're producing. So those, every 100th item might be, you take all of those and that creates your population or your sample. Is everybody okay with that idea? So if I produce 1,000 cars today and I want to, I want a 50 car sample, I take 1,000 to divide it by 50, and then, every 200th car is what I'll sample. Does that make sense? Very easy to execute in practice. Is this random? Not really, but it's still pretty good for a case of like you're manufacturing something. This makes a lot of sense. Would it make as much sense if you're like surveying every 10th person that leaves the grocery store and then try to draw about the city in general? Probably not. Most people's grocery stores tend to be pretty local, so you're probably only really getting individuals from one neighborhood in the entire city. Probably a much worse sampling method there. But in a manufacturing setting, I think this makes a lot of sense. And it's really easy to execute at the end of your assembly line, as opposed to like, of the 1,000 items that we produce today, we're going to survey these random numbered, things off the assembly line, which is hard for the person doing the data gathering to keep track of like what number we're at, as opposed to just like have their little clicker and be like, taking that one, you know what I mean? So another type of sampling is called a cluster sample. So when we do a cluster sample, we're going to separate our individuals into clusters based on like geography, how close they are to one another, like physical space. What's the advantage of doing that? Well, it's not going to be a statistical advantage. It's going to be a monetary advantage. Where if you're trying to survey, like Michigan voters, like it would stink if I did a random generator and I'm driving all over the state, like covering like 20,000 miles trying to track down these individuals, rather than saying, okay, I'm going to take like, 50 suburban voters from this suburb, and then like 50 urban voters from this city, and like 50 rural voters from this small town or whatever. And I'm just going to, I'm just going to be driving around one area instead of like crisscrossing the entire state over and over again, trying to track down random individuals. So it's often like makes it easier on the surveyor to do this kind of thing. You know what I'm saying? Yeah. So it's almost always the cluster sampling is done for cost reasons, because a truly random survey or random sample is so expensive. Like they can be really expensive and time consuming to complete, because if you have like a non-responder, if you're surveying individuals and like your name was the random name drawn and you just can't get this person to respond or even track them down or figure out where they live, are they still alive, like becomes really difficult and really expensive, as opposed to some of these other sampling methods we're going to look at. Almost never do you get like a fully random sampling because of things like that. In the hardest of hard sciences you can, but almost nowhere else is anyone willing to do this. So we've seen how to sample well. How do we sample badly? One of the worst ways of sampling is using what's called a convenience sample. And that's just choosing individuals from the population that are easy to reach. So like, if I ask my friends if they like this show that I like on television, they all say yes, I conclude that everybody must like it. Well, that's a crappy sample, because all you did was ask people with similar interests to you because you're your friends. Or if I survey the rest of the football team and ask them what their favorite sport is, and it's like, oh, football is by far everybody's favorite sport. And it's like, well, you only ask the guys on the football team with you. You know, like, it's not usually a great way of doing things. Now, in reality, what's the advantage of doing a convenient sample, though? It's easy, it's cheap. It's one of the easiest and cheapest ways to sample anything. It's like, let me just look at the stuff that's here that I have access to right now. And there's something to be said for that. You know, like, money is not unlimited. And we've talked about why they might give unrepresentative data. When I do a sample, like if I am asking just my friends what their favorite, you know, if they think this is an awesome TV show or not, that's introducing bias. The bias being that if we're all friends and we kind of like the same stuff and I like this, the odds are they're also going to like this too. Not only that, but they also might be, because they're my friend, might just be willing to agree with me. If you have you know, like you're overestimating then like the popularity of this thing because of the people you chose, your sample would show bias, right? Okay. Another poor kind of sample is called a voluntary response sample. So that's a case where people are, or the individuals decide whether they want to participate in the sample or not. Good example of this would be like an internet poll. Like if you've seen polls on Twitter or whatever, X, I guess is what we're calling it now. Or on, you know, like where you vote on a web page for something. Those are voluntary response samples. Who are the most likely people to respond to something like that? Yeah, the people with strong opinions are the people that are going to respond to those things. Is that going to be a great representative sample? Probably not, right? Now, what's the advantage there? It's easy. You just can put up your website and just sit back and wait, right? Or if it's the case of you know, like like you're doing a political survey, you just mail it, you know, out. You mail out like 100,000 of these things and hope you get 10% of them back. You know, you can do it all by mail or whatever. But a lot of political sampling is done via convenience, because it's really hard to get a hold of somebody that's willing to sit down and answer your questions, either on the phone or in writing in a text message, all that. It's hard. It's really hard to find people that will sit down and answer questions like that. Another type of sampling is quota sampling. So it's similar to the stratified, where you stratify your population, and then you just gather data from each stratum in a non-random manner. So like could be a voluntary response survey, could be a convenience sample, whatever, until you get like 100 responses from that strata, and then you stop collecting. Now, the good thing about a quota sample will be that you can fix your demographics a little bit, right? Because you're guaranteeing to get like 100, get the desired distribution of individuals that meet the criteria for your sample. The bad part is you have all the same bias you would if you used a convenient sample to collect, or if you used a self-response or voluntary response or whatever to collect the individuals inside the stratas. So it's still got all those same problems, even if your demographics look a little bit better and you look more representative on that side. Because it's like, oh, well, it matches the income distribution of the population in general really well. Yeah, but how'd you pick them? You know? Anyway, we kind of talked. I'm mostly talking through how to do these things instead of reading the words. You guys are better with me just talking about than reading the words on the page. Yeah, that's typically more entertaining than, it's like, I can read too, Mr. Kulik. You don't have to say it. So next thing we'll talk about is inference. Again, we've mentioned this already, but inference is drawing conclusions about a population based on the data from a sample. And the reasons why we want random sampling is because it makes our inferences likely valid. So it's more likely to get a valid inference if our sample is randomly selected. By random selection, we typically will avoid bias. And then because of the laws of probability, by that I mean, like, if I flip a coin 10 times, it's not super unlikely that I get like heads 8 times, right? Might say, oh, 80% of the time I get heads. But if I flip that coin 10,000 times, I'm pretty sure that it's, like, I'll feel pretty good at coming out near 50-50, right? So that's the idea here. If I do a random sampling and I take a big enough sample, I can feel pretty good that the result that I'm getting actually is going to match the population, much in the same way as that flipping coin example. So that's that last bullet point, that the larger random samples gives better information about the population. The other piece is that random samples come with a margin of error. If you're interested in politics at all, you hear these, like they have like the presidential race. They're like, so-and-so leads, candidate A leads candidate B by 6% in the state. But what they don't often mention is there's a margin of error that goes along with that might be, 2, 3, 10% or whatever. So if it says candidate A leads candidate B by 6% and the margin of error is 3%, could be that they only lead by 3%, or they could be leading as much as 9%. But it gives you some kind of bound on that number. You're able to do that if you have a random sample, which is often quite helpful. All right. So the other place where we can introduce error or bias into our sampling is not just how we're picking the individuals, but how we're asking the individuals, how we're gathering our data from the individuals in our sample. So say we picked a lovely, perfectly random sample. It's beautiful, it matches, it's great, and we have super high confidence. And then the questions are like, like my least favorite flavor Starburst is orange. What's your least favorite flavor of Starburst? Where I've like preloaded some bias into the question by already stating that like I don't like this flavor. Okay, so that was the wording of questions, right? Another might be under coverage. So we did this perfectly random sample. Maybe we're talking about voting individuals in the United States or eligible voters in the United States. You know who's really hard to get a hold of that are technically eligible voters? The homeless. How are you going to find a homeless person if you're trying to survey them? Really difficult, right? Like, how about voters that don't speak English? Oftentimes, really hard to get in contact with some of these people. So under coverage. Another problem is you have this great random sample. What about all the people that didn't respond? How many of you answer your phone if you don't recognize the number? None of you. None of you will. How are you supposed to, how's like a sampler supposed to get you into their sample to find out if the blue jeans they're planning on marketing are going to be something you'd buy? And then systematic pattern of incorrect responses in a sample survey leads response bias. I need to write down an example for here for this. Okay. So like, okay, here's a good example. You've seen these things where like a school run a contest of like, what should we name our mascot? And then you'll get like a bunch of joke responses in there, right? Like I remember it was like England or somebody had built this new big impressive battleship or something, and they're trying to get people to vote on what the name was going to be. And the top response was like Bodie McBoatface or something. Like that's an example of your response bias where you're getting like systematically wrong. Like nobody's serious that they want like this flagship of the English fleet to be named Bodie McBoatface or something. It's a real thing that happened. It was probably 15 years ago, but that's an example of like response bias. It's like when you get people voting for Mickey Mouse for president or something. You guys get the idea? I don't think so. I think they just scrapped it or picked their own name after they saw some of the other popular names. I don't remember the end of that story though. All right. Next up, I want to do some in-class example questions. So I have some examples based on the stuff we just talked about. Nope, that's the wrong section, dum-dum. That's the one I'm looking for. And oops, come on. Go. Oops, that's not where I wanted that to go. Go back over here. All right. So we're just going to kind of run through. I don't like the way that looks. Oh, come on. Good gracious. Okay. No, I want to click view. That's better. Just do a couple of those. That's better. All right. So we'll do this voluntary response style. that means you can just volunteer to respond. If I have to, I'll make this a simple random response and pull out my random student generator to pull names. So we have a table of data about 10 random US residents from a recent census. Who can tell me the population for this data set? Say it loud if you got it. I heard whisper. Somebody whispered. No. No. No, man. U.S. residents. Yeah, that is the population that we're sampling from. U.S. residents. Everybody's okay? The size of the sample is 10, right? I don't know what 29 would have been. Oh. Okay. Who can tell me the variables that are measured? That's one. That's another. That's another. That's one. That's another. Yup. One more. That's the last one. Everybody cool? Really hard. Which one of those are qualitative? States, good. What else? Married and gender, good. What are quantitative? Age, family members, income, travel time. Perfect. Everybody feel good? These are the kind of things you'll have to do on your quiz or your test or something, right? Like no calculation, just like, oh my gosh, Olivia's gonna freak out. Describe in a sentence the individual in the first row. Should be more than just married, right? That's true. 61 female, who's married, lives in Kentucky.
2 family members.
Yeah. Great. Yes. So just put it all together in a sentence, basically. Ah! It's okay though, right? All right, based on the data, what inferences could you make about the U.S. population in regards to their gender and then to their marital status? No, we're not comparing the two. So based on this survey, what can we say about gender for U.S. residents? Good. Could you be more specific? Can you put a number on the more females than males? How about we say 60% of U.S. residents would be female and 40% of residents are male? Right? Could you say that? Based on the survey, that's not unreasonable. Now, saying more females than males is still fine. That's true. And in fact, that's probably a better inference than the 60-40. Why is the 60-40 not a great inference? Okay, but why? So it's a small sample, right? We're talking about making inference of a sample size of 10 people on a country with what, like 350 million people in it? Not great, Bob. How about marital status? What can we say about the marital status? 70% are married. 20% are single. 10% aren't. Well, we say separated here, but yeah. Or you could say most are married. That's a little better. Again, crappy inference because tiny sample. Everybody feel good? Not too bad, right? Just got to start thinking like a statistician. Next one, it says, in May 2010, the Los Angeles City Council voted to ban most travel and contracts with the state of Arizona to protest Arizona's new immigration enforcement law. The Los Angeles Times conducted an online poll that asked whether the city council is right to pass a boycott of Arizona. The results showed that 96% of the 41,000 plus people in the sample said no. What type of sample did the Times use in this poll? Voluntary response. Excellent. Explain how this sampling method could lead to bias in the poll result. Absolutely. Very good. Almost verbatim of what I would have had written down. A school librarian wants to know the average number of pages in all the books in the library. The library has 20,000 books, arranged by type, fiction, biography, history, and so on 400 shelves. Each shelf holds 50 books. You want to select a random sample of 500 books. How could we select a simple random sample of those 500 books? Good. Assign each of the 20,000 books a number. And then select 500 random numbers from that list. And then you would count up the number of pages of those books and average them. Great. Everybody's good on that? Explain how to select a stratified random sample of 500 books and justify your choice of stratum. Same what? Yes, I think stratifying by genre would be the obvious choice there. Why would you justify that as a reasonable strata to do? Mm-hmm. What are we trying to study here, though? It's the number of pages.
Oh.
Do things in the same genre typically have, like a reference book tends to be pretty meaty. A lot of fiction books are a lot briefer, right? That seems like, stratifying them in that way would be reasonable, right? That would be your justification that things in the same genre, tend to be maybe about the same length. Like a textbook is typically much longer than a novel. Why might the librarian want to choose a stratified random sample instead of using a simple random sample? But why would the librarian want to do it? She's the one that actually has to go find these books and count them. Why is it easier? It's still 500 books worth of pages. Yeah, so if the books are sorted by genre, they're all going to be in the same geographic area. So I can go and find all the fiction ones and then go and find all the, history ones and whatever. Now I still have to they're random pulls from the shelves, but at least I'm not trucking my way back and forth across the library. Mm-hmm. What are the disadvantages, though? Mm-hmm. As opposed to a simple. okay, let's think a little bit deeper into it than that, though. So let's say that, like, I don't know, like 13.5% of our books are fiction, right? So 13.5% of my 500 books should be fiction, right? But that doesn't come out to a whole number. How do I round that, decide how many books, fiction books, I end up really wanting to pull? But if you do that every time, maybe now it's 507 books or something. That's the draw, right? That's the drawback, is that we have these hard choices to make in terms of, okay, what if I'm supposed to take a decimal amount of books from this strata? How do I decide? Should I be rounding up or down to still make sure I end up with 500 books at the end? You know what I mean? That's a tough one. Part C says, explain how to select a systematic sample of 500 books. How would you do a systematic sample for 500 books? So you take the total number of books, which is 20,000, and divide it by the size of your sample. So 20,000 divided by 500 is 200. So every 200th book is going to be our sample. Oh, I'm sorry. That's not right. I did it by 100, not 500. It should be 40. My apologies. Every 40th book will be our sample. Why won't the librarian like this method? It's really simple, right? I just walk down the stacks and every 40th book I pull, right? Easy. What are the disadvantages? It's not really random. And why might that matter? Okay, and the error being that some genres might be overrepresented and some might be underrepresented, because it's possible one of these genres has less than 40 books in it. You could skip it altogether, right? You might skip a genre completely, and it might be just giant, massively long books, and we skipped all of the dictionaries or something. You know what I mean? So that's the risk you run. And you got I got 25 comic books, and I skipped all the dictionaries. You know what I mean? Oops. All right, D says, explain how to select a cluster sample of 500 books. And then justify your choice of clusters. Yeah, what'd you say? Who whispered it? Yeah, the shelves would be your clusters, right? So you have 400 shelves. So you take, so we're going to do the clusters or the shelves. Now what? How about you randomly select 10 shelves and take all 50 books from each shelf? How's that sound? That's a cluster sample for you. We took all the individuals just in a region on one shelf. So we randomly selected the shelves and then all the books on that shelf. That's what we used. What's the advantage? Yeah, it's even less walking, right? I just go to one shelf and I'm just, okay, pull book, pull book, pull book. I don't even have to go anywhere. Right? Super easy. Disadvantage. What else do we know about how the library is organized? All the genres are together, so it's very likely you could really overrepresent, one genre versus another and skip genres altogether, right? Does that make sense, guys? Cool. What do you guys think? Those are our example questions. Notice that the most math we had to do today was divide two numbers. But you had to understand what stuff meant, right? And think about like worst case scenarios and like, how would that work? And this is pretty indicative of like a lot of statistics is kind of the gray area of math where we're not computing anything and you just have to like use your brain a little bit to think about like, what would this look like in the real world? Or like, how would you do this? Or like, what could happen? It's not always this squishy. We definitely get some numbers and we use those numbers to say things. But this stuff that we did today about talking about sampling will be really important for us, specifically when we start working towards our IAs, your internal assessment. What you'll do is you're going to do an experiment. So you're going to sample something, pick a population and do a sampling of it. So understanding what you did and being able to talk about that intelligently in your paper is good, really good. I say this every year and often I get very little about the sampling in papers, but this is good stuff to talk about. It's a good argument for the validity of your inference at the end of the day. If you do a good job of sampling anyway. And if you can't do a good job of sampling because of constraints, then explain that, right? Like I recognize that I did this sampling method, which isn't great, but like my budget for this is $0. All I have is time, So I did the best I could with what I had available to me. And that's a reasonable thing to say, right? Like, just be honest and recognize the limitations of what you were able to do because you're a 17 or 18-year-old that had a $0 budget to do this sampling. You could say what you would like to do in practice, like it would have been much better if I was able to do it this way and describe how you do it. That's awesome. We love that. So understanding like what's good and bad and like what's the pluses and minuses of what you're able to do and what would you do with unlimited budget and resources. That's all.